Hey, welcome. Have you ever looked up at a huge mountain or a skyscraper or even just a really tall tree and thought, how in the world would I figure out how tall that is without actually climbing it? Well, it turns out, with a little bit of math, you can measure pretty much anything from right where you're standing. Today, we're going to unlock the secrets of trigonometry. It's the same tool that's used to map distant stars and build those incredible virtual worlds in video games. We're going to use it to measure the unmeasurable.
So let's just start with that big, kind of impossible-sounding question. How do you measure a mountain? I mean, you can't just throw a giant tape measure up the side, right? It seems like it can't be done. But, people figured this out ages ago, and it all starts with one simple idea.
And believe it or not, the key is right here in this simple picture. It's all about the relationship between you, the flat ground, and the very top of the thing you're looking at. See? It forms a triangle. And that triangle holds all the answers. Let's see how trigonometry lets us crack this puzzle wide open.
But, before we can jump in and solve the puzzle, we got to gather our tools. We need a way to talk about this triangle using the clear, consistent language of math.
So, let's build our official trigonometry toolkit. And don't worry, this isn't going to be complicated. There are just a few really simple concepts we need to get, and once we have them, trust me, we can tackle some seriously impressive measurement problems. Okay, the first tool in our kit is probably the most obvious one, the line of sight. It's exactly what it sounds like, just a straight, imaginary line connecting your eye to whatever you're looking at. This is our basic connection to the object we want to measure. Simple, right?
Next up, we need to talk about the angle. So if you're looking up from a flat horizontal line, like you're looking at the top of that mountain, we call that the angle of elevation. And if you're standing on, say, a balcony and looking down at something, that's the angle of depression. It's the same basic idea, just in a different direction. It all depends on your point of view.
And finally, here they are, the magic keys to our whole toolkit, the trigonometric ratios. You've probably heard of them: sine, cosine, and tangent. Now, these aren't some kind of complicated spells. They're just super simple formulas that connects the angle in a right-angled triangle to the lengths of its sides. Think of them as the bridge that connects the angle you can easily measure to the heights and distances that you can't. They're going to do all the heavy lifting for us.
All right, we've got our toolkit ready. Let's put it to the test. Our first challenge, let's find the height of a tower without ever leaving the ground.
So let's picture this. There's a tower, standing perfectly straight up. We're on the ground, some distance away, and we tilt our head up to look at the very top. Boom. Right there, we've just created a perfect right-angled triangle.
Okay, let's break down what we know. First, we've measured how far we are from the tower, and it's exactly 15 meters. Second, we've used a simple tool to measure the angle we're looking up at, our angle of elevation, and it's 60 degrees. The only thing we don't know is the actual height of the tower.
So which tool do we grab from our kit? Well, think about it. We need the one that connects the angle we know, 60 degrees, to the side we know, the 15 meters, adjacent to us, and the side we want to know, the height, which is opposite the angle. And that is exactly what the tangent ratio does. So we set up this simple equation. The tangent of 60 degrees is equal to the height divided by 15.
And after a quick little calculation, we've got our answer. The height of the tower is 15 times the square root of 3 meters. Just like that, without a single step of climbing, we figured out the exact height of that tower. Pretty cool, huh?
Okay, that wasn't so bad, right? Let's level up and try something a little trickier. What happens if the thing we want to measure is sitting on top of something else, like, say, a flagpole on top of a tall building? Here's the strategy, and it's a classic problem-solving trick. You take one big, complicated problem, and you break it into two smaller, simpler ones. You can see we actually have two triangles here. So first, let's just focus on the smaller one, the one made by the building itself. We'll use our first measurement, that 30-degree angle to the top of the building, to figure out how far away from it we're standing. We know the building is 10 meters tall, so we use our tangent tool again, and it tells us that our distance from the building is 10 times the square root of 3, which is about 17.32 meters. Okay, nice. Part 1 is done. We've got our distance.
And now, this is where it gets interesting. We're going to use that distance we just found. That number, 17.32 meters, becomes a known piece of the puzzle for our second, bigger triangle, the one that goes all the way to the very top of the flagstaff, using that new angle of 45 degrees.
So we set up our second equation. The tangent of 45 degrees equals the total height, that's the building plus the flagstaff, divided by that 17.32 meters we just calculated. And here's a neat little math trick. The tangent of 45 degrees is just 1, so the math is super easy. The total height is also 17.32 meters.
We're on the home stretch now. We know the total height all the way to the top of the flagstaff, and we already know the height of just the building. So all we have to do is a simple subtraction to figure out the height of the flagstaff all by itself.
And there it is. The length of that flagstaff is 7.32 meters. See what we did? We took a pretty complex problem, broke it down into 2 manageable steps, and used our toolkit to solve it piece by piece. Fantastic.
Let's just pause for a second and think about what we just did. We took these kind of abstract ideas, angles and ratios, and used them to measure real, solid objects out there in the world. And once you start looking for them, you start to realize the world is just filled with triangles waiting to be measured.
So what are the big lessons here? Well, first, that any complex-looking problem can usually be broken down into simpler parts. Second, the most important step is almost always just visualizing that hidden right-angled triangle. And finally, those simple little ratios, tan, sine, and cos, they're the keys that unlock everything. They really do let you measure the unmeasurable.
So I'll leave you with this last thought. You now have the basic toolkit that astronomers use to figure out the distance to stars, that game developers use to build 3D worlds, and that architects and surveyors use to build our cities. The next time you see a tall building or a faraway hill, you actually know what it would take to find its height. The only question left is, what are you going to measure first?